Welcome back, everybody, to the fifth season of the online seminar series, Machine Learning Needs Mathematical Optimization. We are extremely pleased today to have Simge Kucukyavuz. She's a professor in the Industrial Engineering and Management Sciences Department at Northwestern University. She's an expert in mixed integer, large scale, and stochastic optimization, and she has applied this to different areas such as logistics, energy, computing, statistical learning, social networks, and so on. So her research has been supported from multiple grants from the National Science Foundation and from the Office of Naval Research. She is the recipient of the 2011 NSF Career Award and co-winner of the 2015 Informs Computing Society Prize. Actually, she has been past chair of this society, and she serves in the editorial boards of many of prestigious journals in our field, such as Mathematics of Operations Research, Mathematical Programming, Science, Journal on Optimization, and so on. And I would like to say that she is also invited as keynote speaker to many of the leading conferences in our field. We are extremely pleased to have you today, Simge, and the floor is yours. And as is usual in this series, if you have urgent questions to the audience, please put them in the chat. Otherwise, we take, say, a Q&A session at the end. Thank you so much, Simge. And
sounds good. Thank you, Dolores, for the nice introduction, and thanks for organizing me. It's so great to reach the other side of the world through the seminar series. So I'm pleased to be here. I woke up to sad news today out of my home in Turkey, so my heart goes out to all those impacted by the earthquake. So today I'm going to talk about a machine learning problem that got me started in this area. That is of learning Bayesian networks. And as Dolores said, my expertise is in integer programming. So we're going to take a second order conic integer programming look at this class of problems. This is my main part of the talk. So mixed integer programming for learning directed acyclic graphs or Bayesian networks. But I also, time permitting, like to take this opportunity to tell you, the series is called Machine Learning Needs Optimization, but also to tell you how optimization can benefit from machine learning. So in the second part of my talk, I'll talk about some of the mixed integer programming theory that we have been advancing inspired by these learning problems and conclude. So let's focus on the learning problem first. So this is joint work with my former student Hassan Manzoor at University of Washington. He's at Amazon now. Ali Shojai is my collaborator. He's a professor in biostats department at University of Washington. And Lin Chuan Wei is my current student at Northwestern, and Hao Xiang is a former student as well. It's going to be a summary of two works, one ongoing and one published in Informs Journal on Optimization. All right, so this class of problems, learning Bayesian networks, it's a problem that arises in probabilistic graphical models. So what the goal here is to represent dependency structures among random variables in the form of a graph. And we'll be especially interested in directed acyclic graphs. So the direction of the arcs or edges will be important. And that's what's known as Bayesian networks. When is this useful? This is used in probabilistic reasoning, causal discovery, prediction, classification, and diagnosis. And a lot of the times these causal discoveries are done with learning from expert knowledge, but this may be costly and non-trivial in certain settings. So what we're trying to do is to learn from continuous observational data. So one application is a classical one, is from 2005 science paper, causal protein signaling network. So where the authors studied the signaling pathway structure of 11 proteins, how they interact with each other, and their dependencies. And as you can see, this is believed to be the Bayesian network underlying the structure, and you can see the directionality in this graph. And you can also see that this is a directed acyclic graph. So because we're looking at dependencies, we do not want cycles in this graph. I'll be more precise in a second. So what is the sort of mathematical definition of this problem? We're given some data matrix, n by m. So we have n samples from m random variables, and these random variables we'll treat as nodes of a graph. And we're trying to understand the effects among the continuous random variables and under a structural equation model, a linear equation model. So it's going to be a series of linear regressions of the following form. So the random variable xk is dependent on the random variables xj, who are parents. So this is my notation. Parents of k in the graph G0, which is the true graph that we're trying to discover. And of course, like in any linear regression model, there's some unexplained variation that is captured with this delta here. So what is unknown here is we're not only doing the linear regression and trying to figure out what the betas should be, we're also trying to understand the graph structure. So what are the parents of a node in this graph for which we should run our linear regressions for each node? So an example graph here. So suppose this red graph is the true directed acyclic graph, G0. Of course, we don't know this. We're trying to figure this out. So in this case, node 1, random variable 1, does not have any parents. So it's just this unexplained variation here. Node 2 depends on node 1. So we see a simple linear regression, and we are trying to figure out now beta 1, 2. On the other hand, node 3 has parents 1 and 2, 2 and 1. So now we're trying to figure out beta 2, 3 and beta 1, 3 in understanding the linear equation given in here. I hope you can see my pointer. System is new to me. So again, perfect. So we're trying to figure out betas, these multipliers, the regressors, and also the arc structure. All right. So what do we start out with? If we don't know anything about our problem, we'll start with a complete undirected graph and try to understand which arcs should exist. And again, we don't need any, you don't want any cycles. But there are some statistical tools. For example, there are good estimators to understand the so-called superstructure graph. We're going to call that calligraphic M. That we can find efficiently and consistently from data. This is usually looking at the empirical covariance matrix and looking at which entries are sufficiently above some threshold. So we could start out with an incomplete graph, as I show here, which is a superstructure, and this is easy to estimate consistently. So if we start out from superstructure graph such as this, we only select arcs among the edges that exist. So we need to find maybe an edge does not exist at all in the graph. And if one edge exists, we need to determine which direction. And as you can see again, there are no cycles in this graph. Again, no known superstructure, then just go with a complete graph. The edges undirected are denoted by E, and if we're starting with the undirected superstructure graph, we're going to duplicate each edge and show it in 2 directions, and that will be the E arrow set. Right? So some things we know from statistics literature. So can we even identify such a DAG? It turns out that there are some results that show that such a DAG is identifiable for Gaussian distributions, or even if it's non-Gaussian, but we have a linear structural equation model as we assume, and homoscedastic noise, which means just equal variance in the noise. Then we know that we can identify such a DAG. And in this same paper, the authors give penalized negative log likelihood model to show that, you know, if you optimize this model, if you find a true optimal solution to this model, as n increases, you will get a consistent estimator. The graph Gn hat will converge to the true graph G0 if you solve this mathematical program. And what is this mathematical program? So we have, so capital B is going to be the matrix of betas. So we have an F beta, which is measuring our fit. So it's originally negative log likelihood, but it can be shown that actually in this case, the negative log likelihood is proportional to squared L2 loss. So it just really becomes this squared convex quadratic optimization function. And usually we're interested in sparse DAG estimation, and in which case we'll have a sparsity parameter theta b, and a penalty function or penalty multiplier lambda. What are the constraints of this model? Well, we're trying to find the graph that induces a DAG from the superstructure M, again, complete if unknown. And this is the regularization, pi is the regularization term. And what the theory suggests is you should be using an L0 regularization. So this is the model the researchers gave. And of course, you know, this is a difficult problem. First of all, there are constraints that have to ensure that the graph is a DAG. We know that this is NP hard already. And then we have this convex quadratic function and L0 regularization. So, so in the statistical literature, you often see, you know, this is a mixed integer program, it's NP hard, and, you know, then, you know, other methods are sought after. Usually there are heuristics to solve this problem, and I'll talk about some alternatives as well as we go on. But we in an integer programming world are not too afraid when a problem is NP hard. We can still solve these problems efficiently, especially in mixed integer linear programming. So we started thinking about how to model this problem as a mixed integer, now convex quadratic problem, and what we may do to be able to solve it. So first of all, we need to capture the DAG constraints. So one way to do this is to use the definitions of DAG. So let me start with the linear order. So a linear ordering of a set S is a permutation of its elements, and you know we use the notation J precedes K if when we use the permutation pi j comes before pi k. This is linear order. Topological order is related. This is for graphs. So topological ordering of the nodes V in graph GVE is a linear order where the order pi j is less than pi k if there's an arc from j to k. So j comes before k. That's the definition of a topological order. And we all know that a directed graph is a DAG if and only if there exists a topological ordering of the nodes. So what we do is we label the nodes in this topological order uniquely from 1 to n if there are n nodes. And again, there's no, the topological order should follow this rule that if there's an arc from j to k, then the label pi j is less than pi k. So there are many ways, for looking at the same DAG, there are many ways to come up with a topological order that satisfies this condition. So it's not unique. And there are existing MIP formulations for the learning problem, Bayesian network learning problem based on these definitions. But when we started this research, they were not as efficient as we would like them to be. So we started thinking about how we can improve the solution times. So here's another DAG definition. First of all, I need to define a layered network. In a layered network, there exists no arc from a layer labeled V to a layer labeled U if U is less than or equal to V. And another way to look at a DAG is that a directed graph is a DAG if and only if it is a layered network. So let me show you with a graph here. So here's a directed acyclic graph of 13 nodes. And we only use 3 labels. The numbers you see are the original node labels, but we have layer numbers. So that's going to be psi j. So we have 3 layers. J psi j equals 1 collects all the nodes that have no incoming nodes to them. So these are sort of the roots, if you will. Layer 2 will only have arcs coming from a layer 1. And layer 3 will have arcs coming from layer 2 and layer 1 as well. So as you can see, there's no backward arc, and a backward arc will create a cycle. So might create a cycle. While a topological ordering of this graph, a DAG, will have many possibilities, you can label this 1, 2, 3, 4, or you can do 4, 3, 2, 1, etc., and many other combinations, and that goes on with the other nodes as well. Whereas a minimal layered network encoding, minimal in the sense that you give them the lowest layer number possible, that is unique. So that gives us an advantage. You know, in integer programming, we worry about symmetry and how that causes difficulties when there are identical solutions that are actually the same. We sort of prefer this option in terms of symmetry. Again, you could use the topological order to come up with layer numbering, but that won't be a minimal one, and it's not unique. So using the layered network idea, we're going to have psi j as variables that denote the layer number of node j. We're going to have variables zjk1 if beta jk, this regression parameter we're trying to estimate, is non-zero. Note that these parameters can be positive or negative. So we have the layered network formulation, f of beta. This includes the little f beta and the regularization term. We have the big M constraint. So the absolute value of beta jk should be less than or equal to some big M times djk. One big problem I'll allude to is how to find a big M. So in these regression type settings, there's no natural big M. And this needs to be taken as quite large. The constraints over here, second set of constraints, make sure that the layer numbers follow the order that we want. So if zjk is 1, there's an arc from j to k, then the layer label of k should be at least 1 greater than the layer number of j. Otherwise, this is another big M type of a constraint. We express this as a constraint, zjk plus zkj less than or equal to 1. But actually, the way to deal with it, this is just to say that you only need to create half of the variables. You don't need both variables here. So the formulation is somewhat compact. So we have constraints that are in the order of number of edges, arcs, I should say, and the binary variables also on the order of the arcs. Okay, so the advantages, these are more compact relaxations, but there are some connections to other like TSP type problems and subtour elimination constraints that have been studied. And it's compact because it's sort of aggregating some of the constraints that you might write for more sort of detailed models of directed acyclicity. But what we show is that with these convex quadratic objective, this relaxation of this formulation does not sacrifice from bound quality. It will give you the same bound as one that would use the so-called stronger formulation. And this comes from the quadratic objective. So BGAM constraint, I showed the absolute value version, but this is how you would sort of open it up in linear fashion, and no natural BGAM value. There are heuristics to find good ones, and they're quite conservative and large. So one thing that we know in recent integer programming research is to use the so-called perspective reformulation to strengthen this BGAM constraint. So I'll introduce what that is if you're not familiar. And this, again, uses the convex quadratic objective. So let me just sort of forget for a moment about the problem, and suppose we are minimizing a function beta square. Beta is our continuous decision variable, and we have the complementarity constraint like we had before. Beta, just one variable for now. Beta times 1 minus z equals 0. What this says is if z is 1, then beta can be anything, positive, negative. But if z is 0, then beta has to be 0. So that's ensuring the BGAM, another way of writing the BGAM constraint, z is 0, 1, and you could have additional constraints. So that's captured over here, which I will omit for a moment. So this is what it looks like. So I'm going to omit this constraints for a moment and look at this set R. Epigraph variable t that will capture t greater than or equal to b beta square. So minimizing beta square is equivalent to minimizing t when t is greater than or equal to beta square. And then the complementarity constraint over here. So if you look at this set, when z is equal to 0, we are over here. T is greater than or equal to 0. We have this tick. And when z is equal to 1, we have t greater than or equal to beta squared. I'm showing 1/2 of this. And we're trying to take the union of these two sets in this simple world. And it is well known in integer programming that the so-called perspective reformulation is ideal for this simple mixed integer convex set. What does that do? So it relaxes the binary requirement to being between 0, 1, and drops the nonlinear complementarity constraint. There's no BGAM constraint either. All it says is that t is greater than or equal to beta square over z. And this is nothing but the perspective function of beta square, beta square with respect to the variable z. And we use the convention that beta square over 0 is 0 if beta is 0. Another way to write this is beta square less than or equal to tz, which is a second order conic formulation. This is a formulation you can enter Gurobi. So we want to benefit from this perspective reformulation. So how do we do that? So the original, so what I showed you is one quadratic term. If you have separable quadratic terms, you will introduce a ti variable for each of them and do this perspective reformulation. One obstacle we faced already is that the objective, when we look at the quadratic loss, is not a separable quadratic. But there again has been research, Frangioni and Gentili, etc., who studied this problem and said we can actually extract a diagonal matrix from this X transpose X matrix, and then have, so the elements of this diagonal matrix will be delta by the delta vector, delta 1 through delta n, and that will be D. And then we sort of extract that separable quadratic terms using this diagonal matrix and its entries, delta j, beta j square. We will have some remainder. The goal is to extract in such a way that the remainder is still maintaining convexity. So this is the way to open that up. And we still have our sort of regularization term. Cycle elimination constraints, from now on, I'll use the layered network formulation, but you can actually try all other formulations as well. And z still binary. Now, I cannot use the convexal result and relax this to be 0, 1 because of this sort of approximation that we've done, as well as the additional constraint that we have for which we need integrality. But at least this could give rise to a stronger formulation. And in fact, that's what we will do. So we will now strengthen this formulation. I represented it in the objective, but we'll actually introduce an epigraph variable tjk for each of these separable quadratic terms and write the second order conic constraint. So we can show that this has stronger bounds than the began formulation. So when we solve the convex relaxation, we'll get a better lower bound. And as I said, this can be represented as a mixed integer second order conic program, and Gurobi has ways to deal with that. Cplex and Gurobi have ways to deal with that, although it's not as advanced as their mixed integer linear programming solvers. So just some quick summary of computations. We, in our both of our papers, we have extensive computational studies, but I'll just give you the gist of it. So we look at the same data set, a celebrated data set from the causal protein signaling network. We solve this problem with the layered network formulation. And a way to measure the accuracy of our estimates is the structural Hamming distance. So try to look for sort of missing edges or arcs that are directing in the wrong direction. This will contribute to the Hamming distance. So lower structural Hamming distance is better. So what we do is if we solve this problem, which is sort of a small problem, so 11 proteins means 11 nodes, the number of samples actually, interestingly, does not matter for the mixed integer programming formulation. This only factors into the calculation of X transpose X matrix that we are entering into our objective. The number of variables and constraints don't depend on this. So we get a structural Hamming distance score of 9, whereas if we use the state-of-the-art heuristics, which at the time were no tears and DAG MLP, we get much higher scores for the structural Hamming distance. So one thing to say here is that the statistical guarantees on consistency and quality of the estimators, remember, are for optimizing that integer program. Whereas heuristics have no guarantees on how, even with respect to the optimization objective, how the quality of the objective function is. And that seems to translate, at least in this instance, to the accuracy of their estimators. And again, this is a mixed integer program. It's NP hard, but for this small problem, it just solves in 2 seconds. So something to sort of convey a message that some integer programs are not as hard as we may think. So there are classes of now, since our first work, there have been some work in statistical literature, state of the art for identifiable instances. These are the instances where we assume equal variance. So there's an approach called top-down approach and a bottom-up approach that are purely statistical. So they solve a sequence of covariance estimates to determine, in the top-down approach, you would try to determine the sort of the root of the DAGs and then move on to, if you want to think about the layers, layer by layer, and bottom-up is to go from the bottom layer to the top. So these run in polynomial time, very efficient algorithms. They have good statistical guarantees for identifiable instances. But if you have non-identifiable instances, meaning your errors have non-equal equal variances, then these algorithms have no guarantees for such instances. They run fast, but there are no statistical guarantees. Whereas the mixed integer second order conic program is guaranteed to find a member of the Markov equivalent class. What this means is, again, at least we can find the skeleton of the graph, the superstructure, a superset of the superstructure efficiently. So we have, again, a lot of comparisons, but I highlight here the non-identifiable instances from sort of known test sets. You see here the number of nodes in the parenthesis. So this is equal variance, DAG estimation, top down. This was the best performer among the state of the art that we tried. So I'm only presenting that in this presentation. You can find more in our working paper. And this is our estimator here using mixed integer second order conic programming. CoreRest is a statistical method to enter the superstructure information that I told you about. So we have a superstructure estimated through this correlation estimator. We feed that into our MISO-CP as a superstructure graph. Again, this state-of-the-art is very fast, polynomial time, and runs really fast. But in these non-identifiable instances, the structural Hamming distance, as you can see, is quite high. So in a 70-node graph, 52 of the edges are wrong, either missing extra or directing in the wrong way. Whereas with mixed integer second order conic programming, we suffer from time. We have a time limit of an hour, and there are 10 instances generated for each of these graphs using the linear structural equation models. But we get better estimators with respect to the structural Hamming distance. This is the structural Hamming distance looking at the skeleton. Because these graphs are non-identifiable, it makes more sense to compare actually the skeletons, and we're doing much better over there for most instances as well, as you can see here. This is the gap when the instances don't solve within the time limit. So the gaps are pretty small. I'll say a word about that in the next slide. And then we have some other statistical metrics, true positive rate, false positive rate, and we're doing better in those aspects as well. So true positive, we want that to be higher. False positive, we want that to be lower. So the method seems to work well, especially for these harder instances of non-identifiability. Another thing we observe, again, I'm just picking one to highlight this. The moral of the story here is that these moral graphs or superstructure graphs are important. So pick a data set, factors data set, and if you start out with a complete graph, you see how the lower bound progresses over time, very slow and flattens out, and the upper bound also stays pretty much the same. And this is an instance where it takes a lot of time, 20,000 seconds, and we still haven't improved the lower bound by much. If we feed the same problem, if we feed a moral graph, you can see that the convergence is much faster. And you also notice that actually this is the optimal solution, and it's found really early in the process. It's just that most of the time is spent on proving optimality and improving the lower bounds. So this gives us research questions, which I will address in the second part of the talk. Another thing we were interested in is one advantage of mixed integer programming compared to the heuristic I talked about is, you can stop it early and there will be some guarantee. If you stop it over here, you will be able to calculate what your gap is. How far are you off from optimality? Maximum sort of gap between where you are and where you want to be. So the question was, can we stop early and still guarantee consistency? So now we use integer programming as a heuristic. We have a time limit, maybe, or a gap limit. And can we still say something that even if I stopped over here, my gap is small enough that my estimators might be good. So here is a complicated looking slide. I just want to show it to you and tell you the gist of it. In our more recent paper, we show that if you look at your optimality gap, this is the absolute optimality gap, which is the difference between the upper bound and the lower bound in the objective. And if it is of a certain order of magnitude that depends on the logarithm of number of nodes in the graph and some estimate on the number of arcs in the true DAG. So you should, we don't know this, of course, so you should use an estimate for this. Then you can show that your estimator beta hat for the regression coefficients is somewhat asymptotically converging to the true estimators at the rate that I show with high probability. Alpha 0 is between a minimum of 0.05 and 4/m. So we ran some experiments on synthetic instances with the stopping condition. So we say, okay, stop the branch and bound process when your gap approaches whatever this estimate for the gap should be. And then, we see that, we can run these mixed integer programs about 32% faster, up to 32% faster. And when we calculate the SHD scores, compare it with the sort of the real estimator, we don't see any difference. So we don't sacrifice from the quality of the estimator. So we saw that sort of pictorially in the factors data set, but we can check the early stopping condition empirically as well. So how am I doing on time? I have 10 more minutes, I think, to try to talk a little bit about this improvement of the lower bounds. So I showed you one way, so use the perspective reformulation that we knew from integer programming research by extracting the diagonal and using just that diagonal separable structure. So this gets me to the second part of my talk, unless there are questions, or I can take the questions later. But just to give you a gist of how this type of research inspired a whole new line of work on my research, which I refer to as learning-inspired MIP theory. So how to strengthen such a formulation. Until this research, I've been looking at mixed integer linear programs, how to strengthen formulations for mixed integer linear programs. And thanks to this class of problems, I started thinking about how to improve formulations of mixed integer convex quadratic programs. So let me tell you the latest work we've done on that. So this is a separate work joint with Alper Atamtürk from UC Berkeley, Andres Gomez at University of Southern California, and my student Lin Chuan. And this is another ongoing work that we have available in preprint. So I just talked to you about the DAG learning problem, but a lot of the statistical learning problems that have some structural constraints can be written in the same form. So we have some f of beta, so some loss function trying to estimate the continuous parameters beta, and then some sparsity penalty here. The BGAM type constraints or the complementarity constraints that tie the binary variables with the continuous variables, and some constraints. So capital Z is a subset of 0, 1 to the n. Some constraints, some combinatorial constraints that are arbitrary for the rest of my talk. Of course, in the first part of my talk, these were the DAG constraints, directed acyclic graph constraints. Again, convex loss function, in this case, it is y. In the case that we've seen with linear regression type constraints, we have a response variable y, a data matrix x. We're trying to estimate beta, and we're looking at the squared loss. And the regularization term could be a sparsity or even L1 penalty. All right, so this is the structure we're interested in. I already talked to you about the interest in DAG learning, but best subset selection, which has a cardinality constraint on the betas, non-zero betas. Multicollinearity prevention is another application where we're trying to choose one out of a subset S to prevent issues with multicollinearity. There are some hierarchy constraints in group variable selection that you might have constraints that select the variable k in your regression only if you selected I as well. And these sort of relationships are defined by logical constraints, combinatorial constraints. So that motivates the different constraints on Z. And we're interested in the quadratic function. So now I'll have a Q matrix to handle the non-separable quadratic terms now. There could be a linear penalty. This could be the L0 penalty represented by this linear term and objective. And there could be also linear terms in the continuous variables as well. We have this constraints that can be either written as big M or this complementarity constraints and constraints on the binary variables based on structure. We'll do the same thing that we've done. So epigraph variable T to capture the convex quadratic, move that to the constraints. So our objective is now linear, one convex quadratic constraints and these original constraints. Of course, again, this is non-linear, non-convex. So typically what you would do is to write a BGAM constraint, and you can now give this, formulate this as a mixed integer convex quadratic problem, but it will have weak continuous relaxations. So in MIP literature, this kind of problem has been studied, but under certain restrictions. So for example, either there's no constraint on Z and a separable objective function. So then that's the perspective formulation that I showed you, and that's ideal. That gives you the convex hull. Keep the Z unconstrained and think of a rank 1 quadratic objective. So let's say summation of beta squared. Then actually perspective formulation is not enough and it can be strengthened. So the constraint looks like this, and this is also second order conic representable. If you consider Z being a single cardinality constraint and separable quadratic objective, that has been studied recently, and you can just do the perspective on the separable terms, and that will be ideal. And recently with Linchuan and Andres, we also showed that take a rank 1 convex objective, and we can give the convex hull for arbitrary Z, but then the convex objective should be rank 1. For example, in the quadratic, it should be in this form. And recently we also said, okay, relax the constraints on Z, but look at the structure on Q. Suppose it's not diagonal, but it's tridiagonal. So it's not quite separable, but it's close to separable. Then we can also give a convex hull description. So in this part, we are now interested in, can we exploit matrix Q and constraint Z to obtain stronger relaxation? And even sort of a more philosophical question, what does strong mean for mixed integer quadratic programming? So we know for mixed integer linear programming, if you can show that inequality is a facet, that's the strongest it can be. But we don't have such a concept in mixed integer quadratic programming. So how can we talk about strong inequalities for mixed integer quadratic programming? And can we leverage polyhedral theory for mixed integer linear programming that tells you this is a facet, translate that to a mixed integer, strong formulations for mixed integer quadratic programming? So let me see, I have 3 minutes for ending 10 minutes before. I think we started a little late, so let me see.
You can take a couple more minutes, don't worry.
Okay, all right. So let me just quickly go over how this works and skip some slides. We really take this generic problem. Q is not necessarily diagonal, no assumptions on Q except that it's positive semi-definite. We take a combinatorial view. Actually, I'm going to assume it's positive definite for now. We take a combinatorial view at it. So take a subset of S, and I'm abusing the notation a little bit. Subset S means a vector Z I is 1 if I is an S, and 0 otherwise. So that will determine, the support of this will determine a subset, and that should belong to the constraint set Z. So the other variables, so remember, if I is not an S, then Z is 0, beta is 0, we can essentially forget about those variables. So we can just rewrite this problem. There shouldn't be an S. This is beta transpose Z. But knowing that Zi is 1 only if I is an S, we can just pose this as a sort of a combinatorial problem of selecting the subset S. And when you select a subset, we're going to use this notation Q of S is the submatrix of Q indexed by S, and similarly AS, BS, beta S. So the original problem becomes that of minimizing over the smaller problem just only in these indices defined by S. So if I were to write this problem, then get rid of the Z variables. This is just an unconstrained quadratic program. It has a closed form solution. It's given over here. Beta S star is minus QS inverse AS. So plug that back in over here, and then you will get a combinatorial view on this, minimize, select subsets S that satisfy whatever your constraints may be, such that you are minimizing, whatever you get after substituting this closed form, which is given over here. Now, of course, this is sort of how do we do this? Because there's a QS inverse, we have to select S subset of Z. So some notation, ES is the indicator vector of S, QS is a S by S submatrix of Q induced by S, and we'll denote QS hat inverse. So you take QS inverse corresponding to the indices of S and fill the rest by 0. So let me give an example. Here, a simple positive definite matrix, D1, D2 greater than 1. If you choose S to be an empty set, obviously QS is 0 and empty, and QS hat inverse will be the 0 matrix. If you choose the first element, then QS is D1, QS inverse is 1 over D1, and then you fill the rest with zeros, etc. So that's how QS at hat inverse works. And so, so this is the main result. I'm going to skip the proof, but essentially what this says is, if you were to able to characterize this polyhedron P, which is nothing but the convex hull of the indicator vectors S and the corresponding QS hat inverse matrices for all S that are feasible. So these are sort of some matrices, matrix variables W, imagine, and vector, in our case, Z. You enumerate all possibilities, you calculate this QS inverse, take the convex hull, that's a polyhedron. So if you knew what that polyhedron looks like, then you can get the convex hull of this non-separable quadratic epigraph term and the complementarity constraints and the Z constraints in the following form. This is essentially an extended formulation. Introduce matrix variables W, M by M. These are going to try and capture the Q hat S inverses. Have one positive semi-definiteness constraint in this following form, a very structured one. W variables, beta are our original variables, and this is the epigraph variable. Formed in this way is positive semi-definite, and Z and W are falling into a polyhedron P. This is the closure of the convex hull. So your problem, the convexification problem, is essentially as easy as characterizing this, as easy or as hard as characterizing this P. So sometimes this is going to be an NP hard case, and sometimes it's easy, so we can get the convex hull. I will skip the proof of this in the interest of time, but it uses the concepts from pseudo inverses. You know, it's not, there's not enough time for me to go through this, so let me flip through. But when can we use this result in closed form? So if you have choose one type of constraints, your Z is such that you can only choose one of your variables, and you have a generic Q, well, because you can choose one of your variables, we already knew the convex hull of this kind of a set. It's just do a perspective on each of the variables using QII, beta I square ZI. We knew this from earlier literature, but it comes us off as a corollary to our main result, because for such a problem, you can find what this P polyhedron looks like. You either choose 0, and in which case your QS inverse is the 0 matrix, or you choose one element at a time, because that's only thing allowed, and you just have 1 over QII as your Q hat inverse filled with zeros, and you can write sort of this convex hull structure that we gave. The positive semi-definite constraint can be simplified, and you get the corollary. How to work with this P in general, especially for hard problems. Again, I won't have enough time, but we can show that we can actually write this as a mixed integer linear formulation. So all the feasible points that satisfy or fall into the convex hull of ES and QS hat inverse can be written as a mixed integer linear program. So it's important to note that this is a linear formulation. Even if it looks nasty and it involves the inverse of this sort of subset of a submatrix. We use a trick that instead of staying in the inverse space, we left multiply the matrix W, which is supposed to capture Q hat in S inverse with Q, and we look at the structure of what that should look like. This gives us linear constraints, logical constraints, whether Zi is 1 if I is an S. So I think I'm over time, but we did do some tests with this mixed integer linear program on a graphical model. This time it's 2-dimensional micro-random fields, a 10 by 10 grid. I know we're out of time, so I'll just show you maybe some surprising results. So original formulation is a big M formulation. It's a very big formula. It starts out with gaps that are incredibly large. These are in percentages. The mixed integer linear program, if you want to look at it. But then it's a mixed integer linear program. Gurobi has ways of dealing with it. It does its magic. We sit back and relax here. We don't need strengthening. And before even branching, it brings the gap down to 0. So this is without doing any Gurobi tricks, and this is after doing the Gurobi tricks at the root node. These problems can be solved, that means we can use polyhedral theory to strengthen these mixed integer quadratic programs. And it doesn't take too much time. Sometimes it's even faster than doing the best perspective formulation. So this is the best perspective formulation with extracting diagonals. And the natural formulation, if you do nothing, it will hit the time limit. It will have an AND gap. So 5 instances out of 5 hit the time limit with positive AND gap. If you do nothing, you can do a perspective trick, or even the mixed integer linear program. So let me just wrap up. We are out of time. So I was interested in these learning problems that opened new possibilities for mixed integer programming research, both in terms of formulating better formulations for learning problems that involve convex quadratic objectives and binary variables. That led to some statistical results tying the optimality guarantees of mixed integer programming to statistical guarantees of consistency and early stopping rules. But again, it really opened up some areas of research inspired by learning in mixed integer programming theory. And so I'm excited to continue this line of work and look at more stronger formulations, and hopefully incorporate these into the software, Gurobi and Cplex, to strengthen their formulations automatically. I'll end here and take questions.
This is fantastic presentation. Thank you so much, Simge. So for the audience, if you have a question, please raise your hand and we will give you a microphone and camera rights. So we have a question from Emmanuel. So Jason, if you can give the rights to Emmanuel.
Thank you for your excellent and impressive presentation, Simge. Very interesting talk. I just have a very low-level question. Can you give us a hint about the etymology of moral graph, of this notion? Why is it called moral?
I see. Good question. I actually don't know where the moral comes from, but I should take a look into it. Yeah, I know.
I was assuming that you could.
Okay. Yeah, I have no knowledge of the history of that terminology. I should find out from my statistician colleague, but yeah, we usually call it superstructure, but it's also known as moral graph.
So this is the notion I also know, but I was a bit struck. But I checked it, and it seems that the graph theorists use it. So there must be a reason.
Yes, exactly.
Consistently.
Yeah, good question. Thank you.
Thank you. Just a side remark, because we are also working on cardinality constraint quadratic problems. It seems that some of the structure you used can also be not by this particular approach, but by probably a similar approach, can be even used for indefinite quadratic optimization terms. So you have you have cardinality constrained continuous, say continuous non-convex quadratic problems under linear constraints plus the cardinality constraint. Or more generally, as you pointed out correctly, complementarity constraints.
Yes.
So it would be interesting to join forces to do this, because I think with your technology, one can get much further than just. I mean, it's a large class, of course, and we know that all the goodness of it are convex, of course, criteria, but still, there could be some applications where we miss this, and then we could still proceed. So thank you very much. I think we should
Thank you.
be contact offline then with this. Thank you.
Yes, yes, I'll be interested to talk to you. I mean, like I said, I already made the jump from linear to convex, so I haven't worked on non-convex myself, but some of my colleagues look at these problems in the non-convex quadratic setting, so without the constraints. So we should be in touch about that and
Thank you much.
talk more about possibilities. Thank you.
Thank you, and thanks to Dolores to provide the community of this great series. Thank you.
Thank you for the questions, Emmanuel. It's great. You are a great contributor. Yeah. So, Simge, I think we, as you say, we are running out of time. As you can see, we have a lot of good comments that people like it, your presentation. Some people are asking whether there are slides. Actually, there is a YouTube video, YouTube channel that we have in NeEDS. So if for the people who are not yet on the mailing list, please join the mailing list and you will receive news about the uploading of the videos. So thank you very, very much. It was a great start of season 5, and I hope to see you face to face very soon.
I hope so as well. And if there's a way to save the questions on the chat, I haven't gotten a chance to see it. This is a new system for me. Otherwise, you can email me. You can just email me those of you who have questions.
Yeah.
All right. Thank you so much. I really enjoyed this, and sorry if I ran over time.
No. You had wonderful material, very relevant to both communities. So thank you so much.
Thank you. Bye.
Bye. Thank you, everybody, and see you next week.